Hi students, have a nice day. Let's continue the equilibrium constants. In the last section we understand that equilibrium constant Kc is equal to concentration of C raised to C D raised to D divided by concentration of A raised to A concentration of B raised to B. So in this section we will discuss more about equilibrium constants. Equilibrium constant for gaseous reactions, etc. First of all, we discuss the variation of equilibrium constant with the variation of equation. Variation of equilibrium constant with the variation of equation. For that, we consider the same equation as we discussed earlier. H2 gas plus I2 gas gives 2HI gas. Okay, this is equation number 1. You take this is equation number 1. For that, the equilibrium constant Kc is equal to, what is Kc for this reaction? Concentration of Hi raised to 2. Okay, Hi raised to 2. It is a gas. You consider the physical state also, divided by reactants, concentration of H2 gas into concentration of I2 gas. Concentration of H2 gas and concentration of I2 gas. This is equilibrium constant for this reaction. We vary the equation. Let's consider the equation 2HI gas gives H2 gas plus I2 gas. H2 gas plus I2 gas. Okay. So for this equation number 2 you put equation number 2. Equation 1 is reversed. Then for that the Kc, let's write K prime or K dash. Okay, Kc is equal to, for this, concentration of H2 gas into concentration of I2 gas divided by concentration of Hi gas square. Okay, here reactants 2Hi, product hydrogen and iodine. So product of product concentration, by considering this general equation, H2 gas raised to 1, I2 gas raised to 1 divided by Hi gas raised to 2. This is equation number 3. Can you observe any relation to these two equations? This equation is the reciprocal of this one, isn't it? You just take the reciprocal. Okay, you just take the reciprocal of this equation. We have H2 and I2 in the numerator, Hi in the denominator. So we can easily write that K prime C is equal to 1 by Kc. K prime is equal to 1 by Kc. When the reaction is reversed, we take the reciprocal of equilibrium constant. That is the conclusion. So here we vary the equation. There is a variation in the equilibrium constant. That's why we discuss this comes under variation of equilibrium constant with the variation of equation. Okay, are you clear about the reverse reaction? When the reaction is reversed, you take the reciprocal of the first reaction equilibrium constant. Here the equilibrium constant for the first reaction Kc is equal to Hi square H2 into I2. Here it is H2, concentration of H2 into I2 divided by Hi square. When the reaction is reversed, the equilibrium constant is reciprocal. Okay, so new equilibrium constant K dash is equal to 1 by Kc. Okay, then for considering the same equation, we multiply with 2. Okay, 2 H2 gas plus 2 I2 gas equilibrium with 4 Hi gas. Multiply with 2, 4. Okay, another equation, you consider the equation number 4. What is the Kc for this equation? K double prime or K2 dash? 2 dash are on the K. So K double dash for this equation is Hi raised to 4 divided by concentration of H2 raised to 2, concentration of H2 raised to, I2 raised to 2. Concentration of H2 raised to 2 and a concentration of I2 raised to 2. Can you see any relationship between these two equations? Okay, I write here, it can be written as, K double prime C is equal to Hi square divided by H2 I2 the whole square. 2 into 2, 4. Okay, 2, then 2. Okay, it is, we can write here. Okay, we consider by reacting this. K double prime is equal to Kc square. Okay, by considering these two relations, K double prime C is equal to Kc square. And what we understand that when we multiply one equation with a suitable coefficient, when we multiply an equation with a coefficient, the equilibrium constant for that reaction is the same power. When we multiply with the 2, the power becomes 2. When we multiply with a 3, the power is 3. And generally we can write that nth power. Okay, finally I will conclude all this. Then again, when we divide the same equation with one number, for example, H2 gas 1 by 2 plus 1 by 2 I2 gas gives 2 by 2, that is 1 Hi gas. So here we divide with a suitable number, that is 2. Then what is the Kc for this? First we reciprocal, second we multiply, third we divide it. What about the Kc? Kc is Hi divided by H2 raised to 1 by 2 into I2 raised to 1 by 2. As the equation is, you know that the equation is Kc for equation Hi raised to 2 divided by concentration of H2 into concentration of I2. This is the equation for first reaction. And by considering these two, what is the relation? It is Hi square divided by H2, once again I write K triple dash C is HI square divided by H2 I2 whole raised to 1 by 2. Good. Apply mathematics. 2 into 1 by 2, 1. 1 into 1 by 2, 1 by 2. Then 1 into 1 by 2, 1 by 2. So 1 by 2 is make us a power. And what is the third relation? When we divide with a suitable number, the equilibrium constant for that reaction is 1 by n, or nth root of the equilibrium constant for the first reaction. All these reactions we concluded. It's a very important for doing problems. All these we concluded in a box, and it is easy to understand. Okay, we make it as a box to easy understanding. A reaction, first word. A reaction, we make it as a box. This is a serial number, SI number. Here are the reactions. Here we can write the equilibrium constant. Okay, first reaction, second reaction, third reaction, and finally the fourth one. This we make a column. Okay, first of all, 1. A moles of A plus B moles of B equilibrium with the C moles of C plus D moles of D. Equilibrium constant Kc. Then we have to write concentration of C raised to C, D raised to D divided by concentration of A raised to A, concentration of B raised to B. And in the second case, the reaction is reversed. C moles of C plus D moles of D equilibrium with A moles of A plus B moles of B. The new equilibrium constant K dash C is equal to 1 divided by Kc. We prove that. Okay. When the reaction is reversed, equilibrium constant is reciprocal. And the third one, when we multiply this equation with a suitable number, Na plus Nbb gives Ncc plus Ndd. N is multiplied to all the reactants and products. And what is the new Kc? New Kc is the nth power of the first Kc. Okay, when the reaction is multiplied with a suitable number, the new equilibrium constant is nth power of the first reaction equilibrium constant. And the fourth case, when we divided the equation by a suitable number n plus b by n b gives c by n c plus d by n d. The number n, the digit n is used to divide. Then what about the new Kc? What about the new Kc? That is the third case. What about the new Kc? It is the nth root of, the nth root of first Kc. Or you can write that Kc is nth root of first Kc. K triple prime, triple dash. This is commonly we used. Commonly used this one. Okay. 1 by nth power, that is nth root. Both are same. Clear? Next is homogeneous equilibrium or homogeneous equilibrium. In an equilibrium, all the reactants and products are in the same phase. It is called a homogeneous equilibrium. Once again, in equilibrium, all the reactants and products are in the same phase. The equilibrium is called a homogeneous equilibrium. Okay, take one example. N2 gas plus H2 gas. Equilibrium method 2NH3 gas. For balancing we write 3H2. It is a homogeneous equilibrium or equilibrium because all the reactants and products are in the gaseous phase. Another example, CH3, COO, C2H5 liquids. Ethyl acetate, an ester, fruity like the smell. Okay, ester is hydrolyzed H2O liquids. H2O liquids is equilibrium with the CH3 COOH liquids plus C2H5OH liquids. Ethyl acetate, ethyl ethanoate. IUPAC name is ethyl ethanoate. Plus water, both are liquids. Acetic acid or ethanoic acid, liquids, liquid phase. Alcohol, ethanol, liquid phase. So here also all the reactants and products are in the same phase. And the third one, Fe2 plus aqueous, or you can take Fe3 plus, no problem. Okay, in your textbook it is 3 plus. Plus 6Cl minus aqueous. 6Cl minus aqueous. Equilibrium with Fe Cn 6 times 3 minus aqueous. Here also all the reactants and products are in the equilibrium state. Sorry, in the same phase. All the reactants and products are in the same phase. So gaseous state, liquid state, aqueous state. So when all the reactants and products are in the same phase, the equilibria is called a homogeneous equilibrium. Next we move to the equilibrium constant for gaseous reactions. Okay, I think you clear about this. You take more examples for homogeneous equilibrium. All the reactants and products are in the same phase. It is called a homogeneous equilibrium. Next we move to the equilibrium constant for gaseous reaction. Okay, equilibrium constant for gaseous reaction. Equilibrium constant for gaseous reaction, Kp. So for gaseous reactants, the equilibrium constant is known as Kp or represented as Kp. Okay, let's consider a gaseous reaction. A moles of A plus B moles of B. A gas, B gas, equilibrium with C moles of C gas plus D moles of D gas. So for this, the equilibrium constant Kp is equal to pressure of C raised to C. Instead of concentration, we consider pressure. Okay, partial pressure. The next term is pressure of D whole raised to D. Concentration of C raised to C, similarly pressure of C raised to C, divided by pressure of A raised to A, pressure of B raised to B. This is the equation. So for gaseous reaction, the Kp, equilibrium constant in terms of pressure, is equal to product of partial pressure of products divided by product of partial pressure of reactants. Okay, let's consider one equation. H2 gas plus I2 gas equilibrium with 2HI gas. 2HI gas. So Kp is equal to pressure of Hi whole raised to 2. Pressure of Hi. This gas, that's why we didn't make it. Okay, we don't write the gas. Pressure of Hi gas raised to 2 divided by pressure of H2 gas into pressure of I2 gas. What about Kc? Kc is concentration of Hi gas raised to 2 divided by concentration of H2 gas into concentration of I2 gas. Are you clear? Yes. So Kp and Kc, Kp is the equilibrium constant in terms of pressure, Kc is equilibrium constant in terms of concentration. Clear? Yes. Next, we discuss about the relationship between Kp and Kc. The relationship between Kp and Kc. Okay, we move to that relationship between Kp and Kc. Again, we consider the same reaction. A moles of A plus B moles of B gives C moles of C plus D moles of D. Okay, same reaction. Again, we consider the same reaction. Okay, first of all, we write the equation. A moles of A plus B moles of B equilibrium with the C moles of C plus D moles of D. What is a Kp and Kc? You know that. So here we consider for ideal gas, PV is equal to nRT. Okay, for ideal gas, the ideal gas equation PV is equal to nRT. Then P is equal to N by V RT. N by V RT. Number of moles per liter, that is concentration. So we can write that P is equal to CRT. Okay, P is equal to CRT. P pressure, C concentration. R is equal to 0.08314 barometer liter per Kelvin mole, or Kelvin inverse, mole inverse. You know that. What is the value of R? Then T is temperature. T is temperature. Okay. Then what about this Kp? Kp for that reaction is pressure of C raised to C, then pressure of D raised to D divided by pressure of A raised to A, pressure of of B raised to B. By considering this equation, we can change this into this table. Okay, I write here Kp is equal to pressure of C is written as concentration of C RT. So concentration of C RT the whole raised to C. This E represents the concentration, remember that. This E represents the product C. Don't confuse it. This is concentration, that's why we write it in square brackets. Another time, concentration of DRT raised to D divided by concentration of ART raised to A. Concentration of BRT raised to B. Clear? So like terms comes together. Okay, make it group together. So concentration of C raised to C, concentration of D raised to D, concentration of C raised to C, concentration of D raised to D into RT is common. Here is RT, here also RT. RT raised to C plus D. Okay, RT raised to C into RT raised to D. Mathematical concept. RT raised to C plus D divided by concentration of A raised to A raised to A into RT raised to A, we will write later. Concentration of B raised to B, like terms group together. B raised to B into RT raised to A, RT raised to B, that is RT raised to B, A plus B. A plus B. Are you clear? Yes. So this is Kp. I derive a general equation. In the textbook, general equation is simply derived. Okay. So Kp is equal to, what about this time? It is Kc. C raised to C, D raised to D, divided by A raised to A, B raised to B is Kc. Then RT is common, so we can write that RT C plus D minus A plus B. So we can write that Kc RT raised to delta N. RT raised to delta N. What is delta N? As you studied in thermodynamics, delta N is number of moles of gaseous product minus number of moles of gaseous reactant. So C plus D, number of moles of gaseous products. C plus D is number of moles of gaseous product. Delta N is number of moles of gaseous product minus number of moles of gaseous reactants. So C plus D is number of moles of gaseous products. A plus B is number of moles of gaseous reactants. Okay, delta N is this. And this is the relationship between Kp is equal to, this is a very important equation. Kp is equal to Kc RT raised to delta N, where delta N is number of gaseous product minus number of gaseous reactants. Clear? This is general equation. You study this equation, not need to derive derivation. If you want, you can study. Okay, it is very good. If you want, you can study, but you should remember this. The relationship between Kp and Kc for a reaction. Okay, gaseous reaction. Kp is equal to Kc RT raised to delta N. Once again, I fastly revise it. For ideal gas, PV is equal to nRT. So P is equal to V comes here, N by V RT. Number of moles per liter is concentration, molarity. Okay, molar concentration. So N by V can be written as C, concentration, molar concentration, RT. Here C is P, you know that pressure, barometer or Pascal or atomic pressure, ATM. C is concentration, R is gas constant, the value is 0.8314 bar liter Kelvin inverse, mole inverse. T is temperature, temperature in Kelvin. Then Kp for this reaction. First of all, we have to write Kp for this reaction, and Kp is in terms of pressure, we write here. Then pressure term becomes converted into concentration terms by using this relation. So pressure C RT raised to C, D RT raised to D. Okay. Then divide by concentration of A RT raised to A, concentration of B RT raised to B. And like terms group together. Similar terms group together. So concentration terms group together. Then RT is common, so RT C plus D, RT raised to C plus D. Then here also RT raised to A plus B. Then C raised to C, D raised to D divided by A raised to A, B raised to B is Kc. Okay, Kc. Then RT C plus D minus A plus B. This is delta N. Change number of moles of product and reactants. So Kp is equal to Kc RT raised to delta N, where delta N is number of moles of gaseous product minus number of moles of gaseous reactants. Okay, let's practice some example to understand relationship between Kp and Kc. Okay, let's practice some examples. I erase this derivation. First of all, we consider H2 gas plus I2 gas gives HI gas. Okay, all are gases. H2 gas plus I2 gas gives 2HI gas. What is the relationship between Kp and Kc? So remember this equation. First of all, you have to find out delta N. Delta N is number of moles of gaseous product minus number of moles of gaseous reactant, 1 plus 1. So delta N is equal to 0. Delta N is equal to 0. Write this equation. Kp is equal to Kc RT raised to delta N, and Kp is equal to Kc RT raised to 0, that is Kp is equal to Kc. If delta N is equal to 0, first condition, okay, if delta N is equal to 0, Kp is equal to Kc, remember that. And the other equation, the second equation, I just erase this, already I write here. Another reaction, N2 gas plus 3H2 gas equilibrium with 2NS3 gas. All these equations we discussed many times. So Kp, so first of all we have to write the delta N. Delta N for this reaction. 2 moles of product, gaseous product, 2 moles. Then 1 plus 3, 4 moles of gaseous reactants. So that is, we can write that minus 2. Delta N is equal to minus 2. We apply into this equation. Kp is equal to Kc RT raised to minus 2. Clear? Kp is equal to Kc RT raised to minus 2. Delta N is minus 2. You just apply it. Then Kp is equal to Kc divided by RT square. Am I right? RT raised to minus 2 becomes in denominator it is RT raised to 2. What it means? Kp is less than Kc. Kc divided by RT square is Kp. So the value of Kp is less than that of Kc. Another equation. 2SO3 gas decomposes gives 2SO2 gas plus O2 gas. An equilibrium is established between 2SO3 gas and 2SO2 gas and O2 gas. Okay, first of all we write delta N. What is delta N for this reaction? It is 2 plus 1, 2 plus 1 minus 2. Are you clear? Yes, that is 1. 3 minus 2. 2 plus 1, 3. 3 minus 2 is equal to 1. Then apply into this equation. Kp is equal to Kc RT raised to 1. Delta N is equal to 1. So Kp is equal to Kc RT raised to 1. So Kp is equal to Kc into RT. R has a value, T, temperature. At a standard temperature also 298 Kelvin. So temperature has a value. So here we can write that Kp is greater than Kc. Okay, here we can write that Kp is greater than Kc. So for competitive examination as well as in board examination, many questions are usually asking from this topic. Give an equation and one of Kc value is given. Kc value is given. What is the Kp value? You follow this method. Okay, Kc value is given. Kc is given. Multiply with the R and T, you get Kp. Similarly, Kp value is given. Find out Kc value. So many questions are usually asking in competitive examination. Okay, so these are the important things about the equilibrium constant. In the next session we will discuss a new topic. Thank you.